This is IAL Edexcel Chemistry. We're going to be covering this part of the specification. It talks about periodic trends. So basically we're going to be talking about certain patterns that repeat within the periodic table. As always, there are notes that come with each lesson. So in my book, this is chapter 6. As you can see, the notes are well written to cover all the little details of the syllabus. So you can see it got all the things that you require to answer exam questions. In addition to the notes, you'll be getting classified exam questions. So they're like more than 50 questions here that are specific to this particular topic. And not only this, because you also have these questions answered. For each question, you do get both the answer and the explanation. My first periodic trend that I'll talk about today is called atomic radius. What does atomic radius stand for? Now, atomic radius is simply the distance from the center of the atom, that is the nucleus here, all the way to the furthest electrons, like the valence electron, which is like the furthest from the nucleus. We have a little problem here. The problem is that atoms are not like perfect circles. Actually, the cloud of electrons is quite blurry, and that makes it very difficult to tell the edge of the atom. Like if the atom was like a circle, it would have been very easy to determine the radius, but here the electrons are in continuous motion. They create a cloud, and the cloud is very blurry, so it makes it really difficult for us to determine the edge of the atom. I want to clarify something here. I want to clarify like how electrons create this cloud. Now, check out this small video here. What do we see? We see a bunch of electrons in yellow. They're rotating very fast around the atom, around the nucleus, I should say. And while they're rotating, they form what we call the electron cloud. So that's the electron cloud I was telling you about there. And our job now is to determine like where is the edge of the atom. Scientists thought about it, like how are we supposed to find the radius of an atom, or like a diameter of an atom? So they thought about it this way. The easiest way to determine the radius of an atom is to put two atoms like side by side and determine the distance from one nucleus to its neighboring nucleus here. Why are we using the nuclei? We're using the nuclei here because it's easy to spot the nucleus. The nucleus is like the densest part of the atom. And we could find this entire distance from this nucleus to this nucleus. And then what do? And then like we could simply divide this distance by 2. It gives us like an estimate of the radius of the atom. So this is like how they found this radius of many atoms, and the rest was based on predicting. So they've used the periodic table, the way we're going to do it today, to find the radius of every atom. What I'm going to do here, I'm going to just show you how the atomic radius, which is like the size of the atom, how does it change down a group. You move like from top of the periodic table all the way to the bottom. Usually, as you are in one group, you'll find that the radius increases. And as you walk across a period, so you take any period in the periodic table, you'll find that the atomic radius actually decreases. So that applies like to all groups. So whatever group you take, the trend will follow. You'll find that it's an increase in the radius. And whatever period you take, you'll find that the radius decreases. So that's something good to remember. But what's more important is like how are you going to explain this? Because that's what really matters. Let's start by explaining the group trend for atomic radius. Usually, if you go down a group, you find that the radius increases, and that's like for one reason. The reason is the number of shells, electron shells, or usually we call them here energy levels. You get more shells and more energy levels you go down any group in the periodic table. So for instance, you take lithium. Lithium is in period 2 of the periodic table, so how many shells you would expect to have here? 1, 2 shells. You take sodium, nucleus, 1 shell, 2 shell, 3 shells. And this continues as you go down any group of the periodic table. So one simple reason why we have an increase in the radius is because we're having more energy levels or more electron shells for each atom in this group. All right, so that's one reason why we have more radius as you go down a group of the periodic table. So now that we explained the group trend, which has to do with the number of energy levels, we're going to move and explain like why is it that the radius decreases as you go across a period. This is mainly because of one important factor, and that is the number of protons. So take any group in the period, take any period, we're talking about periods now. Take lithium on the left and take neon on the right. So like how many protons does lithium have? Lithium has 3 protons. That's like the atomic number. What about neon on the right? It got 10 protons. Now probably you know that protons are positive, electrons are negative, and like you got more protons, then you have more attraction. So like those protons here, what do? They pull the electrons in any atom and they make the radius smaller. So this is what I mean by the nuclear charge or proton number. Now take a look here. What do I have? I have sodium taken from the left side of period 3 in the periodic table and argon on the right side. Take a look at the atomic number or the proton number. So I have an increase, a steady increase in the number of protons, which we also describe as nuclear charge. So since the charge of the nucleus, which is like a positive charge due to protons, since this one increases, what happens to the radius? The radius decreases, right? So like they are inversely proportional. So why does it decrease? Why does the radius decrease? Now think about it this way. The atom has, within the same period, every atom has a specific number of shells. So sodium has 3 shells, 3 energy levels, and argon has 3 shells. So like the number of shells is fixed, but what is increasing here? What is increasing is the nuclear charge. So since I have more protons, then these protons, what are they going to do? They're going to pull the electrons closer, and that makes the atom shrink. That decreases the atomic radius and makes every atom on the right side of the period smaller than the one that comes on the left. So that's like very straightforward trend. There are no exceptions when it comes to atomic radius. Once again, I have elements from the same period. So here I'm taking those elements from sodium all the way to argon, and we're drawing a graph of atomic radius. So remember, as you move across a period, like from left to right, what would happen here? You would notice that the size of the radius or the atom decreases. And that's like, as I told you, it's a steady decrease. And it has always to do with what you say nuclear charge or the number of protons in the nucleus. I am here going to introduce you to some new term. It's called isoelectronic. So iso is like similar, electronic number of electrons. So think about it this way. If you have something like nitrogen, right, and magnesium. Now, nitrogen in the periodic table has 7 protons and 7 electrons. And magnesium got 12 protons or 12 electrons. Now, the ion of magnesium is like Mg2+, right? So if it's Mg2+, this means that the number of electrons in magnesium ion, you have to take away 2 electrons because it's lost them here. the number of electrons there is going to be 10. What about nitrogen? Nitrogen here has 7 electrons. So the nitrogen ion is N3 negative. So that makes the total number of electrons for nitrogen, that would make it also 10. So such atoms that have the same number of electrons, like they're ions actually here, these ions, they have the same number of electrons. What do we call them? We call them isoelectronic, right? So this basically applies to any two species that got the same number of electrons, right? So magnesium ion has 10 electrons, while nitrogen ion has 10 electrons. So how am I gonna figure out which one of these has the smaller radius? It's quite very straightforward. Check the number of protons. The greater the number of protons, remember protons don't change. So the greater the number of protons, that's 12 protons, that's 7 protons. The greater the number of protons, the smaller the radius is. So you're being given two isoelectronic species. The easiest way to find the smaller radius is just figure out which one has more protons. The greater the protons, the smaller the radius is. So right here I have more of those isoelectronic species or ions. So what do I have here? Take a look. So nitrogen ion, oxygen, fluoride, and neon, all of these are isoelectronic. Why they're isoelectronic? Because every single one of these got 10 electrons. How do you figure out the number of electrons? Simply grab your periodic table and think about it this way. Nitrogen ion is N3 negative, so you add 3, it becomes 10. Oxygen ion, oxide, has 8 plus 2, so it's 10. Fluoride, 9 plus 1 is also 10, so F negative has 10 electrons. Even neon, which is an atom, has 10 electrons. What about those metals here? Same applies. Sodium, it's a metal, so it's positive ion. So Na positive is 11 minus 1, that's a 10. Magnesium is also going to have 10 electrons because 12 minus 2 is 10. So how am I supposed to decide which one of those isoelectronic species has the smallest radius? The answer is simple. All you have to do is compare the proton number. So for instance, sodium got 11 protons, magnesium has 12, aluminum has 13 protons, nitrogen has 7, 8, 9, neon has 10. So for that reason, the smallest one of those ions is going to be aluminum. Why? Because it got more protons. Remember, the greater the nuclear charge, the smaller the radius is. All right? So all of these here are isoelectronic because they got the same number of electrons, the same number of shells, and nitrogen is going to be the largest because it has fewest number of protons, while aluminum has the smallest radius because it got the greater number of protons. We're now going to try another trend. So we're going to move from atomic radius to a different periodic trend. So this trend now is called electron shielding. What does electron shielding stand for? It stands for the number of shells of electrons that block the nuclear charge. So take this atom, for example. This is the atom of sodium. Where is the nucleus here? That's the nucleus with all the protons and neutrons inside. Check those electrons in blue. Those inner shell electrons, like this shell, right? They're all blocking the nuclear charge. Why are they blocking the nuclear charge? Because electrons are negative, so they're gonna cancel out the nuclear charge. So having these protons stuck in the nucleus and these electrons in the middle blocking the nuclear charge, what are they gonna do? They're gonna allow this electron to escape easily. The more shells of electrons, right, the greater the shielding is, and is the easier for outer shell electrons or the valence electrons to escape and turn this atom into an ion, right? So again, shielding is quite straightforward. It's just how many shells of electrons you got inside the atom. The greater the shells, the greater the shielding is. We're going to try to combine those two trends that we've studied so far, the radius and shielding. So take a look here. Remember, the radius increases as you go down, and so is shielding, because both are related to the number of shells. What about the radius? Radius decreases as you go from left to right due to the nuclear charge, but shielding doesn't really change. So we don't have much change in electron shielding. It stays more or less similar as you walk across the period, because again, you're having the same number of electron shells, so shielding is not gonna change. So radius decreases as you go across the period, but shielding is more or less equal as you move from left to right. We're now going to introduce a new concept which is known as the effective nuclear charge. The effective nuclear charge is like the number of protons that you have inside the nucleus. So like every atom got a nucleus and there are protons here inside. Now, as you know, those protons pull the electrons wherever these electrons are. However, now the electron shells in the center or around the nucleus here. So check this electron shell, those are doing what? Those are shielding. Those are blocking the nuclear charge. Now, if you have like the atom of Na sodium here and lithium, think about it. Which one of these has more shielding? The obvious answer is sodium, because it got two shells instead of one shell here on the right. Which one of these has more nuclear charge? So in terms of nuclear charge, this one sodium has 11, lithium has just 7 protons. So the nuclear charge of sodium is greater. However, what really matters here is the effective nuclear charge, because those shells of electrons in sodium are actually blocking the nuclear charge. They're making it weaker. So the nuclear charge of sodium is less effective because it got more shielding. So the greater the shielding SH, the lower the effective nuclear charge, ENC, effective nuclear charge, right? So again, lithium got greater effective nuclear charge than sodium despite having fewer protons, despite having 7 protons only. The only reason is lithium has only one shell that is shielding its protons, and that makes the ENC, effective nuclear charge, for sodium greater than that of, the effective nuclear charge of lithium greater than that of sodium, simply because the shielding SH in lithium is lower than that of sodium. We're now gonna try a new trend that's known as the ionization energy. What does ionization energy, IE for short, stands for? Is like how much effort or how much energy it takes to take one electron out at a time from the atom. So what I have here, I have like this atom here, and you can see that I could, with some energy, I could pull away this electron. Right, so this valence electron can be pulled away from the atom. What am I saying? I have to apply energy to take away this electron. That's because the nucleus in the center has positive protons and it's pulling this electron to the center, to the nucleus. But if I apply enough energy, I could pull this electron away from the atom, and this atom suddenly becomes an ion. So that's where the word ionization comes from. All right. So usually you have a proper definition of ionization energy, which is the amount of energy in kilojoules that is required to pull away 1 mole of electrons. So it's like the unit of counting in chemistry is moles, from 1 mole of atoms. We're going to elaborate on the definition of ionization energies. Is one of the important definitions in this chapter. So what do I have here? I have like a generic atom, and what am I going to do here? As always, we're going to apply energy. The this energy is going to be used to take away this electron, and this atom turns now into a cation, a positive ion. So the definition could be written in the form of like an equation. So what do I have here? I have 1 mole of any atom. Notice it has to be in the gaseous state because it's not possible to ionize atoms unless they've been vaporized, unless they've been turned into gas. What am I going to have here on the right side of the equation? I have 1 mole of ions, cations, still in the gaseous phase. And this is the electron that I've removed originally from the atom, right? So again, you can write it in words, the way I told you, 1 mole of electrons pulled away from 1 mole of atoms, or you can write it in the form of an equation, right? We're going to take the concept of ionization energy further here because we're going to try to take away more than 1 electron. So the removal of 1 electron is what I call first ionization energy, IE. If I take away another electron, then I call this second, third, and so on. So like until I remove every single electron from the atom. So that's what we call successive ionization energy. It means like I'm taking away 1 electron at a time until I take away all of the electrons of the atom. What I have here on the left, I have a graph shows what? That shows the successive ionization energies of sodium. Notice something. Notice that the first electron, where is the first electron on the graph? That's the first, which corresponds to this electron here. Notice that this first electron has the least or the lowest ionization energy. It requires the least amount of energy to be removed for one reason. The reason is shielding. Since this electron is very well shielded, then it's quite easier to be removed from the atom. So that's why the first ionization energy is the least one here. What about the second? Second ionization energy is quite higher than the first simply because we moved now to an inner shell. What about the third? Third is going to be greater. Fourth is going to be greater. Fifth is going to be greater, and so on. But there's some little detail that is really important here, which is those gaps you have in this graph. So every time I move from one shell to an inner shell, I have like a jump or have a gap between those ionization energies. As long as I am within the same energy level, the same shell, there is a gradual increase. But suddenly, whenever I jump from like the second shell to the third shell, then I have another jump or I have another gap in these ionization energy. This is quite very useful for us because it helps us to determine the electronic structure or electronic configuration of an atom. So once again, if I remove the first electron, I am here. But once I remove the second, suddenly I observe a gap. I observe a jump, like sudden increase in the ionization energy. If I remove now second, third, fourth, fifth, sixth, seventh, and eighth, so what happens now? All of these are, let's like show gradual increase. But once I go to the innermost shell or the innermost shell, what happens here? I have like very high ionization energy. So like the last electron is the one that has the highest amount of ionization energy. Now I'll tell you something that came once in the exam. They asked the students to plot the ionization energies. Now notice something. Look at the label of the y-axis. We have those ionization energies in logarithmic form. The reason is because there's a huge difference in the ionization energy between the first electron and the last electron. So the numbers are quite varied. So just going to put random number. So if the first one is 100 kilojoules, the eighth one could be like 1 billion, right? 10 to the power 9, right? So that's why in order for us to plot these, we have to use logarithmic form of these ionization energies. So back to the graph of successive ionization energy, we have magnesium here, and take a look at its electron configuration, what do I see here? I have like 3 shells, first shell, second, third. And as we've seen earlier, that every time I move from the outer shell to an inner one, there is a sharp increase in the ionization. So in magnesium, I have 2 valence electrons. Those are the ones that have the least amount of ionization energy. Then once I move to the inner shell, I have this jump. Then when I move to the last or the innermost shell, which is like the center, I have another jump here. So a graph like this would be very helpful because it helps us to predict the number of shells. So how many shells, without looking at the electron or without looking at the diagram, from the graph I could tell that magnesium got 1 shell, 2 shells, and 3 shells, right? And I could tell the number of valence electrons. There's a trick here. So just take a look at the first 2 electrons before the first jump here. So those first 2 electrons, they tell you that the magnesium got 2 valence electrons. We are now going to look at the trends of ionization energy. So we're going to try to relate atomic radius and shielding to ionization energy. So remember, first we said that as you go down any group in the periodic table, the radius R increases because of the number of shells. And so is shielding. Shielding increases for the same reason. What about ionization energy? Ionization energy decreases. Reason? Since I have more shielding and I have more radius, then the distance between the nucleus here and the valence electron is small. I have little shielding in lithium. In potassium, I have more distance and I have more shielding, right? So it's quite simple here. You can use those 2 factors, radius and shielding, to IE, ionization energy, because the greater the radius, the greater the shielding, the easier it is to pull an electron out of the atom, and that would decrease the ionization energy. So I got a graph here of ionization energy for elements in the same group. So all of these elements here belong to group number 2. As you can see here, the first ionization energy would decrease steadily as you go down the second group of the periodic table for the same reason. There's more radius, there's more shielding, all right? And that results in lower ionization energy as you go down any group in the periodic table. We're now going to look at the trend of ionization energy across the periods. Now, I'm going to take several periods of the periodic table all at once. So let's start with just the general trend. Ionization energy, as you go from left to right, you would expect it to increase. What's the reason? The reason here is that shielding across a period is more or less the same. Radius decreases. Effective nuclear charge or nuclear charge in general, this will also increase. The reason is because you got fewer protons on the left and greater protons on the right of every period in the periodic table. So what about ionization energy? So due to all of these 3 factors, this usually comes for 3 marks, those 3 factors result in what? Those result in greater ionization energy. So again, if you've been asked to explain why is it that, let's say, argon got greater ionization energy than sodium, shielding is not changing, the radius is decreasing, and more important, the effective nuclear charge is greater, and that results in greater ionization energy. So usually in any period of the periodic table, the elements that got the highest ionization energy are those all the way on the right, the noble gases. So helium actually got the highest ionization energy in the entire periodic table for 2 reasons. First is smaller radius, smaller than hydrogen. Second, it has twice as many protons as hydrogen, right? So helium got really small radius. Helium has very little shielding. For that reason, it got the highest ionization energy in the entire periodic table. Looking back at my graph of ionization energy across a period, so what do we see here? I told you earlier that helium got greater ionization energy than hydrogen. Notice that the peak for every period, so take every period here, what would you notice? You notice that noble gas got the highest ionization energy for each one of those periods. On the other hand, elements in group 1, these are the ones that have the least ionization energy because those got greater radius and those got fewer protons than everyone else in their periods. Again, generally speaking, the ionization energy will increase steadily if you go from left to right all the way to the noble gases. If you compare any element on the left to that on the right, what would you notice? You would notice that the alkali metals or group 1 elements have the least ionization energy among all of the elements in their period. We got two exceptions for the trends of ionization energy. These exceptions are here for aluminium, like generally speaking, group number 3 or 13 of the periodic table, and the other one comes from the elements in group 16, that's the group of sulfur. So these exceptions are usually wherever you move from group 2 to group 13 or group 3 here, or whenever you move from group 15 to group 16. So we're expecting always here, what are we expecting? We're expecting a steady increase in ionization as we go from left to right. However, whenever we go from this group 2 to group 13, we see a slight decrease, unlike what we're expecting. Same applies whenever we move from group 15 to 16. So we're going to try to explain now why do we have these exceptions. So the first exception here has to do with the electron configuration of aluminium, or generally speaking, group 13 elements. In those elements, we're turning from block S in the periodic table. So this, you remember from the previous class, is known as block S. So you go to this block of the periodic table, this block P. So moving from this block to that block, we find that the electrons of aluminium are slightly further from the nucleus than the electrons of magnesium. So that decreases the ionization energy of aluminium, slightly lower than that of magnesium, unlike what we are expecting. So once again, if you take electrons from magnesium and that of aluminium, you'll find that the electrons of aluminium, the valence electrons here I'm talking about, they're slightly further away from the nucleus than that of magnesium. So take a look here. I was expecting the ionization energy to steadily increase here, but due to the electron configuration of aluminium, I had actually a decrease. You've been asked to explain this. How are you going to explain this? Well, you tell them, well, the electron of aluminium is found in 3p sublevel, and 3p is slightly further from the nucleus than 3s. So for that reason, we have this slight decrease in aluminium. And how are we going to explain the second exception here, the one we have between phosphorus, group 15, and group 16 in sulfur? So we have a small decrease here. We're expecting an increase, but how are we going to explain this? The way we explain it is by the way electrons are distributed in the 3p sublevel. In phosphorus, these electrons are single. So every electron here is single within its orbital. But in sulfur, one of the orbitals got 2 electrons, and these 2 electrons are stuck in a very small space within this orbital, and each one of those electrons is basically repelling the other. So this electron pair repulsion within the same orbital makes it easier for me to pull this electron out, and that decreases the ionization energy. So that's why we have this, what we call electron pair repulsion, responsible for this small dip in ionization energy every time you move from group 15 to group 16. We're going to try a small summary of factors that influence ionization energy. So we're going to try to figure out whether this factor would increase or whether it will decrease ionization energy. So pause the screen and try to think, how will these factors shown here in yellow, how will these affect ionization energy? So let's start with high shielding. The greater the shielding, the greater the blockage of the nuclear charge, so that would lower ionization energy. Opposite applies to high nuclear charge because that would pull electrons and that will increase ionization energy. Low shielding is opposite to high shielding, so it will have opposite effect. Removing unpaired electrons, so the electrons just like that of phosphorus, if the electrons are unpaired, that would make it more difficult for us to pull electrons away. So that would increase the ionization energy. Lower nuclear charge, that would decrease the ionization energy as well. So I should have put this one here. Removing electrons from high energy orbitals, so if you take electrons from further away from the nucleus, that would lower the ionization energy. Removing electrons from low orbitals, so that means you're closer to the nucleus, so that's higher ionization energy. Finally, removing a paired electron. If I have like paired electrons here, this red electrons would be easier to be removed for one reason, because we've said earlier, that's known as electron pair repulsion, just like the case of sulfur. So that would lower the ionization energy. The last trend we're going to be talking about today is melting and boiling points. So like that's a physical property. Now, generally speaking, if you go across a period in the periodic table, what would you notice? You would notice something. You would notice that there is an increase in melting points of all of those metals and metalloids like silicon, and then you have a decrease. So every time you go across the periodic table, what would you notice? You will notice that elements, group 1 is lower than group 2, lower than group 3, and it peaks, the melting point peaks at those macromolecules of group 4, like carbon and silicon. But then we have like a sharp decrease all the way to noble gases. How are we going to explain this? How are we going to explain the physical property? How are we going to explain the increase and then decrease in melting points? So first, the increase has to do with the metallic structure of elements, and the peak here for group 4 has to do with their structure, macromolecular structure. Finally, the decrease has to do with the fact that nonmetals like chlorine, argon, they have weak intermolecular forces. I'm going to go into details about each one of those physical properties. So let's start with metals. Let's start with the first 3 metals in period 3, sodium, magnesium, aluminum. We notice that there is an increase in their melting point and the boiling point. So why is it that sodium has lower melting point than magnesium? This has to do with 2 factors. First is that sodium has larger radius, and second is because sodium only got 1 valence electron. It's a member of group 1, so we'd expect to have just 1 valence electrons. Magnesium has a smaller radius than sodium, and aluminum has the least radius. Opposite applies to the number of valence electrons. So sodium has 1, magnesium has 2, aluminum has 3 valence electrons. The question is, what does valence electron have to do with the melting point? This takes you back to what you've learned in your IGCSE about metallic lattice or metallic structure. Usually describe a metallic lattice as a bunch of cations in a sea of electrons. So the blue sea here represents the electrons, and those represent the metal cations. So the sea of electrons basically glues those cations together, and makes it very hard metallic structure. The greater the number of valence electrons, the stronger these electrostatic force of attraction between the cations and the electrons. So if I had more valence electrons, like aluminium for instance, then I will have greater metallic forces. So the metallic structure, it gets stronger in aluminium because I got plenty of valence electrons. And what do those valence electrons do? Those glue the cations together and make the metallic bond much stronger. Another factor that affects this metallic structure, or the melting point here, is the radius. Aluminium has like a smaller radius than something like sodium. So that makes the density of charge of aluminium, that makes the density much greater than that of sodium. So again, there are two factors that have to do with the higher melting point of aluminium. One, it got plenty of valence electrons, and those are responsible to bind to the cations. And the second is the fact that aluminium is a small cation. Being a small cation, this means that the density of this positive charge is highly focused on the cation. Unlike sodium, where the positive charge is just like 1 plus and is distributed over a larger cation. So again, charge density can be represented by two factors. One is how much is the charge? Like sodium got 1 plus charge, aluminum got 3 plus charge, so the charge is greater. And the size of the atom, sodium has like a large atom, large cation here, and the charge will be distributed over larger volume, and that decreases the charge density. So in other words, the greater the charge density, the higher the melting point is. So we're going to elaborate on the charge density concept here. So once again, I have sodium. Look at the size. I'm going to make it bigger because that's what it really is. So sodium has like larger radius. Sodium got 1 plus charge. That's opposite to aluminium, where I have 3 plus charge and I have a smaller radius. So for that reason, the density of charge in aluminium is greater than that of sodium. As I told you, another factor is the fact that I have here plenty of valence electrons, and that makes the attractions within the lattice of aluminium, that would make it much stronger. Metallic bond is all about how much attraction there is. So if I am trying to melt sodium, you will notice what? You will notice it would take less heat energy to break weaker bonds. But if I try to melt aluminum, it will take me more heat energy because I got stronger metallic bond in aluminum. So we're now going to explain the highest melting point, and that applies to group 4, group 14 in the periodic table. Why is it that members like carbon, silicon of the periodic table have a very high melting point? This has to do with the macromolecular structures for elements in group 4. So carbon in diamond has very high melting point because you got plenty of covalent bonds. Those covalent bonds are really strong, and it takes a lot of heat energy to melt or to break those covalent bonds. It's almost impossible to break 4 covalent bonds per carbon atom, and that makes the melting point of something like diamond and graphite really high. So once again, we'll take a look at diamond here, and we'll try to explain why is it that it has so much melting point. In diamond, every carbon is attached to 4 other carbons. If you try to melt diamond, you really need to break every single one of those strong covalent bonds. So to break those covalent bonds, it takes a lot of thermal energy to break every single one of them, and that's almost impossible. So in diamond, carbons are attached via 4 covalent bonds. So every carbon has 4 other carbons around, and I have to break every single one of these, and that's really difficult. We're still to explain the last part here about the melting point, boiling point in our case here, which has to do with the nonmetals that we have at the end of each period in the periodic table. Here we have to differentiate between what we have as covalent bonds. Covalent bonds are really strong. We saw that in diamond. So like, for instance, if I take an oxygen molecule, oxygen got strong covalent bonds within its molecule. However, oxygen molecules are attached together via what we call intermolecular forces. So the forces between two oxygen molecules is what we call IMF for intermolecular forces. Those are the ones responsible for the low melting point and low boiling point of nonmetals. So the melting boiling points of nonmetals has nothing to do with the covalent bonds. It has to do with those weak intermolecular forces. For instance, hydrogen has a very low boiling point because the intermolecular force here is really weak. So it takes minor amount of heat energy to break that intermolecular force, and that explains why all nonmetals have very, very low boiling points. Here we're going to try to make a summary of all of the trends that we have seen so far today. So let's start with the group trends. If you go down a group in the periodic table, what would you notice? You would notice that shielding increases. That's because you got more shells. The radius increases simply because you got more shells. Effective nuclear charge decreases simply because of shielding. Notice that shielding and effective nuclear charge behave oppositely. What about ionization energy? Ionization energy decreases because of the first three factors. Electronegativity is a trend that we're going to be talking about later on, but I can still talk about melting point. Melting point decreases if you go down any group of the periodic table, specifically when we talk about metals. Metals at the bottom got greater radius than metals on the top. So since like an element like cesium got larger radius than element like lithium, so for that reason the charge density of lithium is much higher than that of cesium, and that explains the higher melting point of lithium. Across the period, trends change as the following. Shielding is more or less the same because we have the same number of energy levels. Effective nuclear charge increases simply because we have more protons. The radius decreases because of the effective nuclear charge. So since I have more protons, then the radius will drop. IE, or ionization energy, is gonna increase simply because of the first three factors. Electronegativity, as I told you, we're gonna talk about this later on in the syllabus, but melting point can be explained here as the following. So we have a sharp increase all the way to carbon because carbon is macromolecule. Then we have a decrease because we're talking about weak intermolecular forces.